Robotics is hitting a new inflection point. Models are starting to remember only the moments that matter, teach themselves missing motor skills, and simulate the world with actual 3D consistency. That matters because long horizon manipulation has usually failed for two reasons. Memory gets noisy, and world models drift across views. What's emerging now is a more efficient stack for real robots. Keep watching, because the details show how these systems decide what to store, what to learn, and what to trust. Let's explore the first paper. Event VLA, Event-Driven Visual Evidence Memory for Long Horizon Vision Language Action Policies. Event VLA from the Shanghai AI Laboratory and universities including the University of Science and Technology of China, Shanghai Jiaotong University, Dalian University of Technology, Tsinghua University, Peking University, and Huawei Technologies, reframes long horizon robotic manipulation as sparse visual evidence memory rather than dense history buffering. Built on Qwen 3, VL, 4B, Instruct with an optimized fine-tuning policy, it combines fixed visual anchors with a keyframe evidence memory module that predicts future keyframe probabilities from transformer hidden states and commits only task-critical frames through thresholding, 1D non-maximum suppression, and FIFO-bounded storage. The paper also introduces RoboTwin MEM, a diagnostic benchmark of 8 strictly non-Markovian simulation tasks with 430 to 1,544 average steps per episode and required intermediate keyframes ranging from 1 to 5 plus 4 real-world bimanual tasks on the ARX A-Cone robot. Across 17 simulation tasks and 4 real-world tasks, Event VLA reports an average success rate gain of plus 40% over prior memory-augmented VLAs. On RoboTwin MEM, it reaches 75.2% versus 18% for visual anchors alone, while on ARMBench, it achieves 67.8%, establishing state-of-the-art performance for conventional memory-oriented manipulation. The key technical novelty is foresight-driven memory writing. Instead of reacting after evidence disappears, the model predicts which future steps will become keyframes and stores those observations before occlusion, enabling robust long-horizon control without a redundant memory bank. Let's explore the second paper, Insight Self-Guided Skill Acquisition via Steerable VLAs. Insight, from Stanford University and Princeton University, reframes vision-language action learning by making a policy steerable at the primitive level and then using a vision-language model, Gemini 3 Flash, to discover and acquire missing primitives without new human demonstrations. The system first auto-segments teleoperated data by aligning VLM-generated primitive plans with gripper transitions, end effector motion, and visual cues, then fine-tunes a Pi 0.5 VLA with LoRa and a learned progress channel. In the second stage, the VLM decomposes a novel task, flags primitive gaps, proposes single-axis parameters for each gap, and filters successful rollouts with oracle checks before retraining the VLA on the newly acquired primitives. On simulation block flipping in Libero, 150 pick-and-place demonstrations were segmented into over 700 primitive episodes, and Insight reached 75% success after 246 acquired primitive rollouts, while an SAC baseline never completed a flip under the same rollout budget. On hardware with a 6DOF U-Factory X-arm, Insight acquired 20 successful twist primitives in 23 trials and 20 successful pour primitives in 31 trials, then achieved 92% success on twisting, 96% on pouring, and 80% on a 1-4. Primitive twist and pour composition compared with 32%, 16%, and 4% for CapEx, and 0% on the Pi 0.5 baseline. The unified policy retained 100% success on original pick-and-place skills, and Insight also learned sweeping from scooping demonstrations, succeeding in 5/5 trials. Let's explore the third paper, PAI World, a 3D consistent world foundation model for robotic manipulation. PAI World, developed by the Institute of AI for Industries at the Chinese Academy of Sciences, extends a DT-based world foundation model into a 3D consistent multi-view simulator for robotic manipulation by combining 2 architectural pieces and 1 geometric training signal, geometry-aware cross-view attention, GeoRope, and Latent 3D REPA distilled from the Frozen Depth Anything 3 model, built on Cosmos. Predict 2, 5, with about 14B parameters and trained on 2, 5M multi-view robot video clips. from Agibot World, RoboMind, Galaxia, RoboTwin, and RoboCoin, it injects camera ray directions and extrinsics into attention while aligning token relations to 3D, aware features, reducing cross-view drift, depth conflict, and texture mismatch. On World Arena, PAI World ranks first with an EWM score of 72.31 and the best motion quality among all entries. And on Agibot, Challenge 2026, it ranks second with an EWM score of 0.8245 while achieving the best scene consistency at 0.9041. On the Agibot World Text Condition benchmark, it reaches SSIM 0.7683, LPIPSS 0.1844, FID 45.04, FVD 175.7778, and the Medri R14,2, improving geometric reconstruction error by 10% over the next best method. Ablations show the full system cuts MET3R from 16.84 to 14.2, a 2.64 gain that is larger than using cross-view attention or REPA alone, confirming that explicit inter-view communication and 3D prior supervision are both necessary. That's a wrap on today's AI paper highlights. Thanks for watching.